Ik heb net gehoord dat Gijs hoe lang geleden op de wereld gekomen is. Hè?
Iets meer dan 25 jaar.
Iets meer dan 25 jaar. En nu is hij bereid de wereld in te gaan. Hè? Hij staat er helemaal klaar voor. Hij gaat praten over macro-economische modellen in het Laplace-domein. En jullie zouden vergeten zijn als jullie dachten dat je hier in de plek bent, want het is gewoon een werktuigbouwkunde. En nergens in deze titel zie ik werktuigbouwkunde staan. Maar dat is dus zo speciaal aan de groep die wij hier hebben. Wij kijken naar economische systemen precies dezelfde manier waarop een werktuigbouwkundige naar een mechanisch systeem. Hè? Dus wij gebruiken geen economische wetten. Economen hebben geen idee waar we het over hebben. Hè? En wij kijken naar de flow van goederen, hetzelfde als we naar de snelheid van een massa kijken. De hoeveelheid vraag, op dezelfde manier als we naar traagheid kijken. En dat soort dingen. Prijs als momenten. Nou, dat is een leuk idee, maar dat moet wel uitgevoerd worden. En een van de dingen die Gijs gedaan heeft, is precies dat, om dat uit te voeren. En ik ga niet zeggen hoe hij dat gedaan heeft, dat gaat hij zelf zeggen. Dus ik geef je gelijk het woord. Gijs.
Well, thank you, Matt. I will give him a presentation in English. Because I'll be presenting my thesis titled Design and Analysis of Macroeconomic Model in the Laplace domain, and I'll be using an economic engineering approach. Well, economic engineering is provides a price dynamic framework which we analogous to Newtonian mechanics. And with this framework, we can design economic models analogous to dynamical systems. And as control engineers are accustomed to, you can represent these systems using a state-space representation. And also in economics, or for economic engineering, this is intuitive as it gives us the prices and the stocks of an economy. However, there are also alternative representations we can use to represent these dynamical systems, and especially Laplace domain representation. And in mechanics, this allows us to analyze the frequency-dependent behavior. And moreover, it allows us to simplify the mathematical analysis as linear differential equations are transformed into algebraic equations. This really motivates establishing the economic analogs to Laplace domain techniques to leverage these possibilities for economic analysis. And to do this, or to demonstrate the effectiveness of this, I've developed a macroeconomic model. And using this alternative representation, I'm able to analyze economic discounting. I'm going to analyze the business cycle. And I'll be showing what the bullwhip effect is, which is a supply chain phenomenon. And also, this allows me to design macroeconomic models, and especially using a bottom-up modeling approach. So, really, before you can understand or how to model economic systems in the Laplace domain, you must first understand the economic interpretation of the Laplace transform. And the Laplace transform transforms a function of time, ft, to a function of the Laplace variable s, f of s. And this variable s, this is a complex number. Well, for strictly real values of this number, the Laplace transform reduces to the following equation. And this is actually identical to the discounted cash flow method in economics. And what this allows you to do in economics is it allows you to calculate the net present value of a cash flow. In this case, the cash flow is ft. And you discount this to account for the time preference using a discount rate sigma. And then you sum over all future cash flows, find the present value of your cash flow. Well, the Laplace transform really is a generalization of this method, as it not only allows you to detrend, but also to retrend. And therefore, it's better to think of it as detrending instead of discounting. And also, it can be applied to any type of economic time series, and not only cash flows. And therefore, instead of the net present value, f of sigma can better be interpreted as a net present value of a present, net present value function. Well, Well, you might be asking, what is the Laplace transform for the strictly imaginary values? And in this case, it reduces to the one-sided Fourier transform. And similarly, the Fourier transform allows us to, not only in economics, but also in mechanics, to cyclically or detrend a signal. So how does it roughly going to work? You see the red economic time series, and then we decompose it in all its different cyclical frequencies. Well, the Laplace transform takes these two operations and combines it and allows us to detrend a economic time series in real and cyclical trends. And therefore we think of it as cyclical detrending, and f of s can be thought of as a complex present value function. Well, now that we know this, we're going to take this to analyze an economic system, which is in this case a trader, which is modeled in the upper left corner. And this trader we model using economic engineering theory as a mass, and it really functions as a demander. So it demands goods, and it has an output, I, Y, which is equivalent to the price. And on this agent works a exogenous desire, which is equivalent to a force. And this trader, he can trade with a perfectly inelastic market. So this market is not influenced by these exogenous desires, which we model using a wall. And the trades are intermediated by a broker, which is modeled using a damper. And if we would simulate a impulse response to this exogenous desire U in the time domain, we would see the following, that the agent really exponentially converges to its equilibrium price, in this case, 0. And this rate with which this happens is quantified by the discount rate, which is in this case determined by the inelasticity of the agent and the broker, the trade friction of the broker. Well, we can also look at the system in the frequency domain. And we do this by taking an input-output perspective, where U is the input, Y is the output. Then subsequently, we can use these signals and transform these to the Laplace domain, getting U of S and Y of S. Then dividing the output by the input, we find a transfer function, which is a representation of the system in the frequency domain. Well, from this transfer function, we can plot the poles, which in this case equivalent to the discount rate in a complex trend map. And well, let's pause a moment and really think what did we just do? By taking this alternative representation, we were able to summarize this behavior in the time domain and plot it using a single point in the frequency domain. And thereby really more efficiently representing this agent or this agent behavior. And the reason why this is because of the generalized uncertainty principle. And this tells us really that information cannot be localized simultaneously in the time or frequency domain. So in this case, it takes me an infinite amount of time to describe this behavior. So I know it's localized in the frequency domain instead. Well, we can also do this for another type of agent, in this case a dealer, which is almost identical to the trader I just showed you. However, we've now replaced this broker, which introduced trade friction, for a dealer, which has a storage. And economically, this system would, constantly over and understock its inventory forever, as there's no, dissipation. So this system never comes to an equilibrium. And we can quantify this, the amplitude and the, especially the frequency or duration of the this cycle using the inventory cycle in economics. Well, taking the same approach as I just showed you, we can also look at this system in the Laplace domain, deriving the transfer function and plotting the poles. And then we find the following discount rates. However, these are imaginary. And these tell us that the imaginary, this tells us the imaginary axis gives us the cyclical behavior of an agent, and the real axis gives us the discounting behavior of economic agents. So this really were two examples of theoretical systems. However, we can also take these techniques to apply to a more involved system. In this case, a model of the economy. And the model you can see here down below, to the left. And it's a typical circular flow diagram you see in macroeconomics, and it consists out of three agents. In this case, the government, the households and the firms in yellow. And there's four markets modeled: the commodity market, the labor market, the capital market, and the financial market. So I'm going to do this really quick. The agents we model using inductors or masses, you can see in yellow. And we assume in each market there are brokers and dealers, which we model using capacitors and resistors or springs and dampers. So roughly, you get four markets, each consisting out of a mass spring damping system or LCR system, which gives us an eighth order system of the economy. Using the same process as before, we can plot the complex discount rates of this system in a complex trend map, and then we can analyze it. So just as before, we can look at the real parts of these complex discount rates. And what we see is that each market has a own real discount rate. And this really corresponds to the ideas of Keynes, which is a really famous economist, that each market in an economy has its own rate of interest. Also, we see that there's one imaginary valued complex discount rate, which has an inventory cycle. And this behavior we can interpret in macroeconomics as the business cycle. And for more complicated systems, there can be multiple cycles of multiple frequencies. Moreover, we can look at the natural response of the system. So this is simply plotting the responses of each individual complex discount rate. And then we would see that this would consist out of real and cyclical trends. What this tells us is that the business cycle is really endogenous to economic systems, not imposed by exogenous demand and supply shocks. And also, since all these poles are located in the left half of the complex plane, we know the system is asymptotically stable, which means that all the states of the system converge to zero, or in this case, equilibrium, telling us the system is actually competitive equilibrium. Well, this is already quite an achievement, and we went to with this model to Rabobank, and we had a discussion. So really, they thought it was really an interesting model, but they asked us, well, actually, we want more, and specifically one thing. They were really interested in supply chain dynamics and how they could integrate this into their macroeconomic models. And we told them, yes, we can do this, and especially we can do this using Laplace domain. And again, I'm going through this pretty quick. So for details, I refer you to my thesis. We're taking bottom-up modeling approach, starting from the individual electrical components that represent economic processes. From these processes, we can subsequently design, for instance, a trader, which is a type of agent. Then these traders we can interconnect in various ways to model various types of economic interactions. Then we can combine these interactions into a network, in this case, a supply chain network. And then, this is supply chain. Then we can take our model of the economy we just had, and in this commodity market, which you see here on the left, we can then integrate this model of the supply chain. And this allows us to include this supply chain dynamics in the existing framework or macroeconomic model that we already had. Well, to understand what the effects are of what we just did, we can analyze again this system in the Laplace domain. And we do this by looking again at the transfer function, in this case from the flow of inputs of goods and services to the prices of the goods and services. So you can see again the complex trend maps of the system without supply chains and the system with supply chains. And the system without supply chains really looks like a lot like the model I just showed you. So there's a few complex valued discount rates and some real valued discount rates. Looking at the economy without supply chain, within this cone, you can see the same poles and zero of complex discount rates as for the economy without supply chains. But also you see this like banana-shaped band of complex discount rates, which are a result of the introduction of the supply chains. And instead of looking at the real and imaginary values of these complex discount rates, as I just did, we can also use a coordinate transformation and look at the angle or polar coordinates of these complex discount rates, where the angle is quantified by the discount propensity, the damping rate, and the radius is equal to the inventory cycle. And if we do this, as we know that for discount propensities smaller than 1, systems are underdamped. And then we have this cyclical behavior that starts to occur in dynamic systems. This is exactly the effect which causes this business cycle behavior we've seen earlier. However, on top of that, we get another effect for discount rates smaller than 1 divided by the square root of 2, which is known in mechanics as resonance. And resonance really causes an amplification of the signal, which is flowing through, going through this propagates through the system. And to really grasp this, this causes the Boole effect. And to grasp this better, I can show it using another plot, which is known as a Bode plot. This is also a frequency domain figure. So we're looking at the same transfer function. However, now we're plotting both the magnitude and the phase. And what we've done, if we've served the system with a cyclical demand input for a whole range of frequencies. So very slow frequencies, which might correspond to yearly disturbances, and very fast frequencies, which might correspond to hourly or daily disturbances, which are plotted from the left to the right. At least the magnitude plot really gives a measure of how much the signal or the input is amplified or attenuated as it propagates through the system. And the phase gives us how much the output leads or lags the input signal. So looking at the economy without supply chains, which you see in orange, we see a general sloping curve downwards. And this is what we would expect. So as a disturbance duration is longer, its effect on the price really is larger because it's more time to change the price. And for really short duration shocks, we expect price movements to be slower. This is exactly what we see in the magnitude plot. As the frequency increases or the duration decreases, this amplification reduces. For the economy without supply chains, we see something different. Especially, we see some resonance peaks. So this is the peaks in the magnitude plot. And what these tell us really are that there's demand amplification at specific cycles. This is exactly the phenomenon described by the Boole effect, namely that at certain frequencies, there is amplification of demand as a demand shock propagates through a supply chain. So really, where does this come from? Well, to understand this, we can look at the phase plot. And if we investigate this phase plot, we see that these resonance peaks coincide with a phase lead of the system. And economically, this phase lead tells us that preemptively agents react to a demand shock by increasing their price. And this is associated with speculative behavior. And this is actually one of the explanations given in supply chain literature for the causes of the Boole effect. However, we've been able to show it using a real a deterministic model. So, in this thesis, I've developed the economic analogs to Laplace domain techniques. And this really allows us to analyze, first of all, economic time series. using trend analysis. And this is done using the complex discounting analysis to the Laplace transform. But also we're able to analyze economic systems. And we've been able to show effects such as economic discounting, also the business cycle and the bullwhip effect. Moreover, we've been able to visualize these effects using the complex trend map, but also the Bode plots I just showed. And together, this really allows us to, well, to better understand economic models and understand what oranges are of complex economic phenomena. And this eventually leads to an improved predictive performance. And in addition, the mathematical simplification of Laplace domain techniques allow us to design economic models from the bottom up. And this led to emergent behavior. So behavior originating from the interactions of individual agents, manifesting it on a macroeconomic level. This is really a long-standing issue with macroeconomic models that they've long been searching to integrate, and also can provide predictive performance, gains in predictive performance in the future. So for future research, I've only really scratched the surface here for what the potential are of Laplace domain techniques for macroeconomic modeling or economic modeling. I showed you in one of my earlier slides that the Laplace transform can be thought of as a generalization of a valuation method. Well, we can further generalize these valuation methods, and thereby we are able to integrate or to value capital for cyclical trends. Moreover, we are able to use the generalized uncertainty principle I just mentioned to really formalize under what conditions we can best value capital in the time domain or in frequency domain. And there's also a large field of application for Laplace domain techniques for linear control theory. Since you might have noticed, we're from systems and control, and I've only done the modeling. There's also the control applications. And this really allows us within economic engineering to integrate active agents or price makers in economics. And I've given a small example here on the left. So the model of the economy, we can, this could be one of the models I just showed you. Then we could include this central bank, which is a controller. And then we could design this controller to, for instance, mimic monetary policy. And this really is we're able to achieve this only using these Laplace domain techniques, leverage, for instance, loop shaping or pole placement techniques. Well, thank you.
Thank you, thanks for a very limited presentation. What's going to happen is we have a committee consisting of Nori Tavassi from Civil Engineering, who is an expert on transportation and logistics, Koen Hutters from us, who is an expert on economic engineering and economic network theory, and of course myself. And they'll be asking Gijs some questions in a separate defense. However, before that starts, you are tasked to ask him some questions on more general knowledge. So I'd like to open the floor. Ik kan het in het Nederlands doen, geloof ik.
Ja.
Dus, je hebt me zo aangespoord om Engels te praten. Dus we komen allemaal gewoon netjes in het Nederlands. En ja, vraag. Ja, vraag.
Ja, heel mooi verhaal. Zo betekent jullie een aantal voorbeelden zien waarbij het economische model gevalideerd wordt. Dus bepaalde effecten die ook vanuit de economische theorie bekend zijn.
Ja.
Is het ook mogelijk om jouw model bijvoorbeeld deze theorie te kalibreren aan echte data? Om vertrouwen te geven dat het echt de werkelijkheid kan beschrijven?
Ja, dat is zeker mogelijk. En dat heet dan binnen ons veld System Identification. En daarmee is het eigenlijk hetzelfde als dat doen voor blackbox modellen, die veelal in economie gebruikt worden. En het enige voorwaarde daarvoor is eigenlijk dat we wel kausaal gedreven data hebben. Dus wat doe ik daarmee? Dat dus een input daadwerkelijk de drijver is van een verandering in het systeem. En ter ligt er nog wel praktische limitaties om die volgende stap te zetten. Dus dat je echt die juiste input-output relatie gaat vinden in je modellen. Dat is al een stuk makkelijker als je kijkt naar iets meer geïsoleerde systemen. Zoals misschien een oliemarkt waar je heel duidelijk supply of demand stokken hebt door kartelgedreven gedrag. En dan wat lastiger in een macro-economisch systeem. Maar in principe niet onmogelijk. Dus om je vraag om samen te vatten, ja dat kan. Maar dus wel met de nodige praktische. Beantwoord dat de vraag? Ja.
Hebben we nog vragen?
Ja.
Ja, ook bedankt voor je verhaal. Je gaf aan dat je overleg had met de Rabobank.
Ja.
Tijdens zouden zij ook het eerste bedrijf zijn die dit soort modellen zouden gaan gebruiken? Of missen zij daar misschien de technische achtergrond?
Om het eerste deel van je vraag te beantwoorden. In principe is het de applicatie is heel breed. We zetten hier eigenlijk een framework neer wat je niet zozeer alleen macro-economische modellen kan gebruiken om te analyseren, maar heel veel type economische modellen. Dus inderdaad grote institutionele bedrijven die kennis nodig hebben van de werking van de macro-economische systemen, die zouden hier vooral gebaat bij zijn. Of ze de kennis hebben om het ook echt daadwerkelijk te gebruiken. Max zegt altijd het heet economic engineering, met de nadruk dus dat economic het bijvoeglijk naamwoord is. Want uiteindelijk zijn we wel echt ingenieurs. En je moet echt de kennis hebben vanuit van die achtergrond om deze techniek uiteindelijk toe te kunnen passen. Zoals ik zelf natuurlijk ook die achtergrond heb. Dus ja, dat is nog wel een stap die men moet maken.
Oké.
Ja?
Ja, ik vind het even in navolging op deze vraag. Hè. Gaat een Rabobank wel gebruiken? Dat heeft ook iets te maken met in welke mate begrijpen ze het nou echt? Nou heb ik echt heel erg mijn best gedaan als econoom om te luisteren. Maar soms denk ik echt ook, het gaat mij even boven mijn bed. En dan, waar ik werk, zeggen we dan altijd, hoe leg ik het nou uit aan mijn moeder? En zou je me nou eens kunnen uitleggen, want dat gaat ook helpen om mogelijk iets heel krachtigs te gaan adopteren. Hoe kan je nou in lekentaal heel compact samenvatten wat echt de kracht is van wat jij gedaan hebt?
Natuurlijk. De essentie zit er echt in dat wij uiteindelijk bouwen een model, net zoals ieder ander die een economisch die iets wil analyseren. En wij doen dat met economic engineering. En een van de resultaten die we hebben is dat we specifiek een alternatieve representatie van het model kunnen maken, waardoor we bepaalde inzichten kunnen vergaren. En dat zijn die voorbeelden die ik laten zien, waarbij we dus die reële trends en die cyclische gedrag kunnen onderscheiden uit die systemen. En de modellen die economen gebruiken, kunnen dat gewoon niet, zijn structureel niet geschikt om die technieken toe te passen. Dat is wat wij hier eigenlijk doen. We stellen dus die range aan mogelijkheden die we in engineering hebben, die voegen we eigenlijk toe aan de portefeuille van de econoom, waarmee we dus echt nieuwe inzichten kunnen vergaren. En om dat echt te begrijpen, moet je uiteraard wel de achtergrond leren van de economische kant. Maar ik denk, als je in ieder geval de interesse weet te wekken, dat er op zich heel veel welwillendheid is om die stappen te zetten. Ja?
Ik was je al kwijt op slide 7. Dus ja, als je nu kijkt in de context van de afgelopen 2 jaar, Gijs, als je daar nu kijkt van welke ontwikkelingen je zelf hebt doorgemaakt en waar je vandaag aan de dag staat. Wat is dan in de afgelopen 2 jaar je kracht geweest en je valkuil? En zijn zo
dit project heb ik wel met heel veel passie gedaan. Tenminste, ik heel erg gedreven ook vanuit mijn interesse. Ik vond het heel leuk dat ik iets kon doen wat eigenlijk beetje out of the book voelde voor wat ik eigenlijk gestudeerd heb. En dat is denk ik altijd een hele grote drijfveer geweest. En ik denk wat ik lastig heb, wat mijn valkuilen zijn, is toch ook begrenzen, zeg maar, op een gegeven moment dan zeggen, oké, dit is genoeg. En dat op zich heeft dat wel, is dat aan elkaar gelinkt natuurlijk. En ik denk dat uiteindelijk, dat ik heel tevreden hier sta met het resultaat dat ik heb kunnen afleveren. Maar dat het nog best wel moeilijk was om op een gegeven moment op dat punt te komen van oké, ik ben blij met wat ik heb gedaan. En nu ben ik hier. Ja. Ja.
Zou het kunnen dat een goede toepassing van dit soort modellen kan zijn om te voorspellen wat de reactie van een economie is op nog nooit eerder voorgekomen evenementen, black swan evenementen zoals de coronacrisis, oorlog. Dus is dat iets waar het wat meer zou kunnen verbeteren?
Ja, uiteindelijk wat deze modellen echt ook aan toevoegen, wat ik zei, is dat begrip. En uiteindelijk leidt dat tot betere, als je het dus ook kwantitatief weet fitten op data, leidt dat tot veel betere voorspellingen. En daarnaast heb je, het zijn eigenlijk gewoon mechanische systemen. En wij zijn heel goed in designen. Dus we kunnen heel goed kijken van in ons systeem, we stoppen hier een extra veer in, of hier stoppen hier een extra massa. En dan een soort van what-if scenario's uitvoeren waarin we kunnen simuleren, dit verandert en dit is het gedrag dat we verwachten. En dat zou je in principe kunnen doortrekken naar economische systemen. Waarbij je echt gaat designen op misschien een markt die nog helemaal niet bestaat. Wat toevallig ook een van de projecten min of meer inhoudt die hier in de groep lopen. Dus ik weet beantwoord dat je vraag.
Ja, zeker.